it's my distinctive honor and pleasure to introduce Stephen Wolfram, who is one of the great creative geniuses really in the whole domain of computational thinking. Many people around the world every day use his products, Mathematica, Wolfram Alpha, Wolfram Language. He has also made a very ambitious and sophisticated proposal for a new kind of science developed in a book called A New Kind of Science. There's not many people in the world as we know it about whom it can be said that he also literally gave words to aliens, but Stephen has also literally given words to aliens in the movie Arrival, which is actually a really good movie to watch. So the articulation of this is the man here. So this is why, without further ado, please join me in welcoming Stephen Wolfram, who will talk, and I'll forget you talk at something very ambitious, the end of...
Oh, it was a very punchy title.
Yeah, I know. So
the End of Human Exceptionalism. Question mark is important.
Please join me in welcoming.
Well, I've spent about 40 years kind of developing sort of a layer of computational intelligence that can be applied to lots of kinds of things in the world. Sort of the goal is to take what computation makes possible and kind of merge it with the knowledge that we've accumulated in our civilization to kind of automate as much as can be automated, to kind of let humans operate at a level sort of above what we have been successful in automating. And it's been fairly satisfying to see that that's worked pretty well. With Mathematica, which came out 30 years ago now, we kind of took things like theoretical physics and mathematical sciences from something where people didn't think computers could be useful to them to something where people routinely use computers. We've seen the same type of thing happening with various kinds of decision making actually through the kind of computational knowledge that we've accumulated in things like Wolfram Alpha, both in the public sphere and also in private organizations. Maybe you've seen Wolfram Alpha. I don't know, a decent fraction of people in your demographic. So who here has used Wolfram Alpha? Okay, it's interesting. So if I ask that to certain other demographics, I will get 100%. So that's all right. Well, it's what powers the knowledge system in Siri, for example. Also, so if you ever ask Siri knowledge questions, it goes to Wolfram Alpha. So maybe I should. So the point of Wolfram Alpha is to know stuff about the world. I'm afraid I'm running this through my phone in my pocket, so maybe it's slow. But let's just see. So we could ask it. Oh, it's awful slow. But anyway, we could ask it some question that might be some kind of techie question like that. Or we could ask it something like, what is the population of Cambridge, let's say? And probably it will see whether it figures out, okay. So it figured out that we probably meant Cambridge, Massachusetts, because it knows the geolocation of my phone and so on. And so it tells us the answer. Okay, it's interesting. There must have been some change around 1900 there. So we could say, for example, what's the population of Cambridge divided by, I don't know, New York City here? And the goal is to be able to take human natural language and understand it well enough that we can interpret it and compute answers from it. And there are lots of different things you can do. I mean, I can say something like, I say ISS, okay, we'll probably think that might be the space station, and it will use a combination of real-time data about the orbital elements of the space station together with actual computations in celestial mechanics to figure out, okay, that's where the space station is right now, and it can tell us probably it'll, okay, it's below the horizon. Okay, it thinks we're in New York City because that's where it thinks my phone is. So we've been, so the goal of Wolfram Alpha is to be able to take essentially any kind of question that is in principle answerable by kind of knowledge that we've accumulated and make it sort of automatic to answer that question. Anyway, that's a piece of technology that I've been involved in building. It's built on top of a thing we call Wolfram Language, which I'll talk about a bunch more later. Wolfram Language is kind of when in Wolfram Alpha you're kind of communicating with it in human natural language. But what it's doing is converting that human natural language to a precise symbolic language that represents knowledge about the world and then it knows a lot of stuff about the world and knows how to compute a lot of stuff about the world. It takes that symbolic language, does a computation, then gives us the results. In fact, as it happens in Wolfram language, that's the symbolic language that's inside Wolfram Alpha, we've been kind of leaders in the world of modern machine learning, and I can probably show you some things about that later. But anyway, I spend much of my time doing practical things, but I've also spent some part of my life doing basic science. I sort of alternate between doing basic science and technology. I haven't really ever officially done philosophy. My mother happened to be a philosophy professor in Oxford, and so when I was a kid I said, there's one thing I'll never do when I'm grown up, it's be a philosopher. But as it turns out, a decent fraction of what I do ends up being essentially turning philosophy into code. So it's funny how that works out. All right, so I wanted to talk a bit about implications of some of the science and technology that I've done for questions in philosophy and particularly in ethics. So I have to talk a little bit about a big science project that I did. That has to do with how we describe the world, and it sort of led me to a bunch of realizations about the world that were certainly very unexpected to me and have a lot of implications about how one thinks about things like intelligence and so on. So kind of when one thinks about exact science, the kind of tradition from about 300 years ago is if you want to do exact science about the world, you write down a mathematical equation that will describe how the world works. You compute from there. That was the kind of Galileo and Newton type tradition. That works pretty well for lots of kinds of things. It gave us a lot of current engineering, all those kinds of things. But I got interested many years ago now in how one can generalize that. In other words, if one wants to make models of the world, but why do those models have to correspond to the things that have been invented in human mathematics? What is the most general category of modeling that one can do about the world? And so I realized that actually we have a good metaphor for that now. It's programs. Programs can represent arbitrary collections of rules. If we believe that there are theories about the world, there should be rules that govern how the world works. How can we represent kind of general theories about the world? So programs are a good way of representing general theories about the world. And so then the question is, well, okay, so if nature, for example, if the world operates according to things like programs, what kinds of programs might they be? What kinds of programs might physics have chosen to use? What kinds of programs might be operating effectively in the social domain and so on? So a basic science question that then comes up is, okay, well, what do typical simple programs actually do? And turns out there isn't a kind of science that's about that, and that's why I wrote a book called The New Kind of Science, whose foundation is kind of studying the sort of computational universe of possible programs and what they do. So let me show you a little bit about that. So my kind of favorite, this is obviously, I'm a user of my own dog food, so this is just a Wolfram language notebook. Can you see that in the back, by the way? Yeah. Okay, so this is a very simple program, and here are its rules. The program just deals with a line of black and white cells, and at each step it just says, look at the cell above, look at the cell in the middle, cells to the left and right, based on those cells, determine what the color of the cell will be on the next step. Okay, so now the question is, what does this do if we run it a while? Okay, so let's say we started off from just one black cell here, and we run it for like 30 steps, and let's just see let's just give it a mesh just so we can see what's going on. Okay, so that's what it does. So we start off from one black cell at the top there, and this rule does something really quite trivial. So simple rule, simple behavior, kind of what you would expect. Okay, let's change the rule a bit. Let's choose this rule here. Now we run it, started off from one black cell, that's what it does. Change the rule again. Let's say it's this. Do this. Okay, that's what it does. So a little bit more complicated, a little bit more intricate. If we just run this, say let's take that thing, run it for 300 steps, get rid of that mesh, it'll make that nice nested pattern. So it's a very intricate pattern, but it's still a very regular pattern. Okay, so then the question is, if you just look out in this computational universe of all possible programs, what's out there? Here are three examples. Let's just do a kind of systematic computer experiment and just find out what's out there in this world of possible simple programs. So we can do that. It's gotten pretty easy to do that these days. Let's see. Let me see. We can just number these rules. numbering scheme. Okay, so let's say rules 0 to 63. Okay, so each of these is kind of a different possible set of rules for how something might work in the world. And many of them, the behavior is really simple. You start off from one black cell, just dies out, or it just tools across the screen at a constant speed and so on. But every so often you'll see one of these nice nested patterns. And then if you keep going, you get to rule 30 here. This is my all-time favorite. You started off from just one black cell at the top there, and that's the behavior you get. Okay, so let's run that a little bit longer. Here we go. So there it is. So this is a very surprising thing, because this started off, the rule that this uses, we can just show the rule here, very simple rule, started off from just one black cell at the top, and yet you get this very elaborate behavior. Okay, so this is, I first discovered this in the early 1980s, and it's sort of a super surprising thing. It kind of breaks one's intuition, because usually one thinks, if you want to build something this complicated, there has to be some complicated explanation, a lot of effort that you went to. Turns out in the computational universe, that's just not true. There's great complexity easily to be found. The main reason we haven't seen it is because, and I'll talk about this a bunch more later, is that in our own efforts at doing engineering and things like that, we tend to avoid stuff like this because it's not something where we can readily foresee every step of what's going to happen. Okay, well, so let's just take a look. Let's look at another one of these. Let's say, I'll pick another rule that has these ones have 2 colors. I'll pick a rule that happens to have 3 colors, just because it's easier to see some things in that. Let's see what I can do here. And let's make this, let's say, give it some initial condition there. Okay, so here's a rule where it starts off, and after not very many steps, it just dies out, becomes very simple. Okay, let's say we just pick. Let me just do this. Let's say 100 random values here. Let's run it for 300 steps. Okay. So what's this guy going to do? What's going to happen? So it's kind of tooling around here. It seems to be. Well, don't know what it's going to do. I picked up these random numbers, so we should be able to run them again. Let's do this. I set those random numbers to R, so let's run this again. Okay, it'll always be the same every time, it's just a deterministic rule. Let's say we run it for 1,000 steps now. Okay, let's see what it's going to do. All right, what's going to happen? Is it going to get boring, or is it going to kind of come back to life and do something exciting? Is it going to surprise us somehow? What is going to happen? Okay, still can't tell. All right, let's run it for, let's go a little bit further. Let's run it for 3,000 steps. Okay, I'm pretty sure it's going to figure out what it's going to decide what to do and just do it. Let's see. What's going to happen? Okay, it finally died out. Okay, what's interesting about this? Well, it's when we look at this, it's very hard to predict what it's going to do. In fact, the only real way we get to do it is to just, we can run it, we can see what it does, but we can't go from the beginning and immediately say what's going to happen. I might say, by the way, just as an aside, I talked about the motivation for kind of studying programs as the sort of universe of simple programs. Turns out that programs have become sort of the dominant source of models for things in the world. For like 300 years, mathematical equations were, when people said, I want to make a model of something in the world, they'd pick an equation. Last 15 years or so, it's kind of cool to see, for me at least, that programs have won out. That is, when people are making a new model of something in the world, they'll describe it in terms of a program, not in terms of an equation. So programs are good models of things in the world, and that kind of motivates studying, sort of thinking about what's out there in the world of all possible programs. Well, the question, as we start talking about this thing, we can very quickly anthropomorphize, what's it going to do, how's it going to decide what to do, all this kind of thing. And it kind of makes you quickly, when you deal with these things a lot, you quickly start ending up thinking them a bit like minds or something. Okay, what's sort of the basis of that? And what is there kind of a scientific analog of what's going on there? So there's something that I call the principle of computational equivalence, which is the thing that really surprised me, but that I came up with in the early 90s. So it's the following thing. So if you say, if you look at different kinds of systems in the world, and you think of what they do as being corresponding to computations, there's a question of how do those computations compare? So, for example, you might say, well, there's brains, and they do all kinds of sophisticated computations, and there's these little programs here that just have little, things about bits and so on. Surely the brains must be doing some much more sophisticated kind of computation than this thing with a bunch of bits here. Well, the surprising thing is that when you look at the universe of simple programs and so on, you discover that actually above some pretty low threshold, all these programs seem to be equivalent in the kind of sophistication of the computations they do. So one consequence of that, this is a general sort of scientific or even kind of somewhat beyond scientific principle, this idea that when you look at sort of things governed by rules, as soon as you get out of the domain of things where you can readily see and predict what they're going to do, you very quickly end up with things where the level of computational sophistication that of their behavior is the same as all these other kinds of things. So there's sort of a definite universal level of computational behavior. So this principle of computational equivalence has all kinds of predictions. So an example of a prediction is this. It says, if you look at these simple programs, so by the way, one thing we've sort of seen before along the same lines is the idea of universal computing, which originally emerged in the 1930s, though it didn't really get clarified until probably the 1980s. You might have thought, you want to do different kinds of computations. You want to add numbers up. You want to compute some combinatorial problem, or you want to play chess or whatever. That each of these different operations would need a different kind of computer, a different piece of computer hardware. But the thing that was discovered with Turing machines and all this kind of thing is no, actually, you can make a universal computer that can be simply programmed to do all these different tasks. So one of the predictions of the principle of computational equivalence is that universal computation should be ubiquitous. One might think that to make a universal computer, you have to go lots of effort. You have to build a CPU chip with 1 billion transistors in it, all those kinds of things. But the principle of computational equivalence says that isn't true. And if you just look out in the computational universe, you should find universal computation all over the place. And in fact, we know some examples where that's true. We know one of these very simple rules. In fact, let's see, I can show it to you. This one, rule 110. We know that this one is a universal computer. I can run it a little bit longer. And we know it's actually another one of these cases where it's kind of hard to see what it's going to do. Even just starting from one black cell here. But anyway, we know that this is a universal computer. We know the simplest universal Turing machine, which turns out also to be very simple. So we're getting all kinds of evidence for this principle of computational equivalence from its predictions about sort of facts about universal computation. Okay, so what's the consequence of principle of computational equivalence for things in general? What it suggests is that if you look at all kinds of different things that might exist in the universe, in the physical universe, or that might exist in kind of the computational universe of things that we can construct with rules, then this notion of sort of computational sophistication, we quickly saturate this notion. And we don't get to say there's a whole hierarchy where sort of brains are at the top and little programs are at the bottom and so on. Instead, all these different things are computationally equivalent. And so that has, there's a sort of common aphorism, the weather has a mind of its own. People say, oh, that's some animistic, pre-scientific notion. But actually, it has a perfectly reasonable meaning. The weather is operating according to, equations of hydrodynamics. It's actually, you can model it nicely with these cellular automata if you want to, but it's operating according to certain rules. And the statement from the principle of computational equivalence is that actually the computational sophistication of what's going on in the weather is just the same as the computational sophistication of what's going on in these simple programs, and it's just the same as the computational sophistication of what's going on in brains. So there's lots to say about this, and there's lots of things. Okay, here's when you think about extraterrestrial intelligence, for example, you can get yourself quickly. This sort of principle of computational equivalence implies a bunch of things about that. So you might say, gosh, we're the only entities that have achieved this very high level of computational sophistication. It's just not true. But the difference is we then have to be talking about, we have a pulsar that's generating radio pulses, and it's generating very complicated radio pulses because the magnetosphere of the pulsar is a little bit like the weather on our planet. It's kind of got a mind of its own, and it's computing all kinds of things. say, well, that's not really something, that's not really intelligence, that's just some physical process that's going on. Well, unfortunately, our brains are also just a physical process that's going on. So we don't get to use that as kind of the distinguishing feature. You say, but well, the pulsar doesn't really have a purpose in what it's doing. We have a purpose. Okay. Well, that's okay. So I don't usually talk to philosophers, but I'm kind of figuring with philosophers, people laugh quickly when you describe this, when you start describing this issue. But the point is that almost anything can be described either by mechanism. You can have descriptions of why things happen that happen by mechanism or by sort of purpose. You can say, when I throw this ball, it's satisfying, it's following certain equations of motion, it's moving one step to the next, and so on. I'm going to, go through this parabola. Or you can say it's following the principle of least action. It has the purpose of minimizing the action integral for the trajectory of that ball. And so you quickly realize that there's that you don't get to have this thing has a purpose and this one doesn't. Actually, there's more to say about that. There's some fairly interesting kind of mathematical thinking that you can do about definitions of purpose. But for us, the main point here is that in this sort of computational universe of possible programs, the part that corresponds to us, we have a purpose. We think we have a purpose because we have these things, these goals that we have that come from our whole sort of history and evolution of our civilization and so on. And those, to us, seem very obviously to be that sort of a very obvious thread of purpose that we follow. I'm kind of shortening this discussion because I'm trying to get to a bunch of other things I'm saying, but there's much more to say about this, and if you're interested, I'm happy to talk more about it. But basically, this whole question of whether we can think of intelligence and so on as being the sort of essence of human specialness, I think the answer is that we cannot. It's kind of the Copernican moment for intelligence. That is, it used to be the case that we thought, physically, the Earth was at the center of the universe, et cetera, et cetera, et cetera. Well, sorry, that doesn't happen to be true. We might have thought that our intelligence was at some kind of pinnacle of possible achievement in the universe, but that's also not true. So what's interesting is that the thing that is, it means that there's sort of this sort of ocean of possible computation out there, and it's insofar as there's something special about us, it's because we have a particular special history that is all of the kind of the things that we've done in our sort of biological evolution and our cultural progression and so on. Well, it's okay. So here's another way of thinking about this, kind of a little thought experiment. If you imagine kind of the future of humanity, and you say, okay, we're all getting nice augmentation through digital means, and eventually, it'll be technically feasible to upload our consciousness, whatever that means, into some purely digital form. And eventually, the sort of future of humanity looks like, it's a box of 1 trillion souls, basically. It's some digital thing where the operations of 1 trillion souls are going on in the sort of digital matrix that exists there. So then the question is, okay, so we've got this box of 1 trillion souls, and maybe it's a very optimized box. So it's got, the motions of individual electrons are determining the sort of the thoughts of those trillion souls. And then you say, well, okay, we've got this box here, and it's got all these electrons whizzing around and so on. And then next to the box, there's a rock. And the rock also has a bunch of electrons whizzing around, and they have certain behavior as well. And the question is, what is how do we compare? Why is the box of 1 trillion souls somehow more notable than the rock? And one of the consequences of this principle of computational equivalence is you can't look to say, oh, there's a lot more sophisticated computation going on in the box of 1 trillion souls that's the future of human civilization. So what you have to start talking about is things like, well, you can see a thread of purpose that has kind of gone into that box of 1 trillion souls that came out of the whole sort of historical progression of civilization. And so it's sort of interesting to see, you might say, I don't know, when you think about this kind of outcome for humanity, it's kind of like, okay, so the end of history is there's 1 trillion souls in a box playing video games for the rest of eternity, so to speak. And that seems like kind of a bad outcome, But what's sort of interesting to think about is when you think about the progression of human purpose through history, it's interesting to think about things we do today and trying to explain those things to a person from, let's say, 1,000 years ago. You know, I walked on a treadmill this morning. Why? Oh, because I'm trying to do this, I'm trying to do that. It's a whole chain of discussion about why that's the case. And anyway, my tendency is to think that at any moment in sort of the progression of things, one will end up having sort of a local purpose that seems meaningful. But anyway, I'm sorry, I'm darting around between lots of different topics, all of which could be talked about in great detail. But let's talk about, I want to talk more about AI and ethics and so on, because that's the big topic here. So let's talk about technology and what technology sort of is. I mean, technology is basically about harnessing what exists in the world to achieve human goals. That's sort of the meta purpose of technology. And so a lot of technology in the past has been harnessing the physical world, you know, mining, you know, iron, discovering you can make magnets out of it, doing things, you know, finding liquid crystals, finding out you could make computer displays out of them. We can also mine the computational universe, and we can find useful algorithms in the computational universe, and I've spent a lot of time, in fact, many of the algorithms that power things like Wolfram Alpha were found simply by searching the computational universe and finding little programs like this that turn out to do something that's really useful for understanding natural language or for processing images or whatever else. And it's, in fact, modern machine learning has a version of that. I've particularly been interested in searching the sort of computational universe of possible programs without any incrementalism. In modern machine learning, one is using essentially calculus to incrementally evolve sort of the things one wants to achieve the objectives one wants. I've been more interested in like, forget what you think is out there, forget the sort of incrementally what's out there, just look at everything that's out there. But it's sort of the same idea. You end up with these programs that sort of exist in the computational universe and that we manage to mine for particular useful human purposes. And so the real thing is there's this sort of ocean of computational capability out there, and the question is, how do we harness it for human purposes? In other words, how do we take this sort of, how do we tame this sort of ocean of computational possibilities and map it into human goals? Or in other words, how do we sort of tell the AIs what to do? And so I personally have spent much of my life actually as a computer language designer, and in some sense, the goal there, when you build a computational language, the goal is to be able to take human thoughts, to bridge between human thoughts and human goals and what computers can do. So you're interested in, can you make a computational language which humans can understand, humans can express themselves in, and computers can then, as automatically as possible, execute what the humans want. So that's kind of the that's the goal, and you know, if I can start to I don't know, I could say let's say I make I just start asking my language to do things. You know, I might say there's a random graph, show me, you know, communities in that graph, or I might say something like let's do this. Let's say we can talk about the actual world. So this is an important feature of this language, is that it's a symbolic language that can represent things about the world. So New York City is just a thing it can represent, like, you know, like a number, like 23. New York City is just a thing, and we could say, what is the way the computer thinks about that thing? Well, it's this entity that's a city, et cetera, et cetera, et cetera. We could say something like, you know, what's the population of New York City, or something like this, tell us. Or we could say something like, so actually this is sort of interesting to see. If I say something like capital cities in Europe, okay? So that's natural language. It will then go ahead and interpret that as its precise symbolic language from which it can compute the answer. And now I could say, you know, make a plot of where those cities are, and I could compute, you know, distances between those cities or whatever else I want to do. And, you know, we've accumulated an awful lot of data about the world. So if I don't know what, let's do another thing. Let's say something like, well, let's say, how about, let's say Van Gogh. And let's say something like notable artworks of Van Gogh. We can then, so we'll get some list of things, and maybe we can say take the first 10 of those, and then we could say, let's get pictures of those, and then we could, okay, we have most of them. So we could say things like, we could start making, let's see what happens. I'll just say, let's do this. Let's try and plot those in a feature space plot. Okay, that wasn't very exciting. That was kind of trying to distinguish, if we put more pictures in there, we probably would have seen different styles of painting that were used and so on. So this is kind of the, and the goal is to be able to compute about everything, and to have a precise symbolic representation of sort of things in the world. So we might say, you know, hamburger plus fries. That probably, okay, there we go. It's an entity instance of various foods. We can compute things about it. We can go, look, here we go, food type hamburger, et cetera, et cetera, et cetera. So we can then you know, do computations on things like food. So we can do computations on lots of kinds of things about the world. So many of these computations are done, you know, with algorithms. Some of them we can also do. Let's say we pick up an image here. Let's see, there's an image. Let's see whether we can identify, you know, what is that image of. So now this is using modern machine learning. Okay, great. It says it's a person. If we're curious, actually, we can say, you know, how does it figure that out? And we could say, let's take this, and well, actually, let's just look here. This is the neural net that actually does that that image identification. We can go and drill down and see all its details here. We can, for example, go ahead and take that picture. Let's run it. See what it says. Oh wow, to give a different answer and a silly one. But we could just say, just take the first 10 layers in that neural net and just see what the thing is sort of thinking at. So let's see what I have to do with that. Now I could say this, and so now it's going to show me kind of the discrimination, the things it's sort of what's inside the brain of the AI, so to speak, as it's trying to figure out that that's a person or a swimming cap or some other silly thing. Okay, so what I've been interested in doing for a long time is building this kind of computational language that provides a bridge between kind of the things that we might be able to formulate in our minds and the things that computers can do. And you know, that turns into a very big language. You know, in English there are about, you know, maybe 50,000 reasonably common words. In our computational language, there are about 6,000 sort of core kinds of things that one can deal with, whether it's about geometry or about sounds or about geographic data or properties of the weather or whatever else. And this is sort of attempting to map kind of knowledge about the world and thinking about the world to what we can actually compute with. And I think it's sort of an important thing for education that we now have. You know, we talk about teaching people to do sort of computational thinking. Computational thinking is kind of the paradigm of these decades, so to speak. You know, back in the past, people, when they wanted to sort of formulate things precisely, they would think about turning to mathematics to do that. The age we're in now, you know, for every field of human endeavor X, there either is now a computational X or there soon will be. And it's kind of thinking about things in the computational terms that you need to sort of do computational X for all X is kind of what we're interested in doing. And with like the language that I've spent a few decades making, we're finally to the point where it's possible for sort of humans, that things are automated enough that kind of even the kids can kind of tell the AIs what to do, so to speak. Well, so in a sense, this sort of form of intelligence that we have in this form of computational intelligence that we have, this sort of it's the first example of alien intelligence, and it's as I've been talking about, the thing that, you know, this sort of disembodied notion of intelligence is all over, is everywhere. But what's relevant to us is intelligence that we can relate to, and for that we need some kind of shared computational language that lets us tell that sort of all those tell that computational universe what we want it to do. So one of the things that we might like is to teach the AIs, so to speak, things like our ethics. We might want to tell the AIs, be nice to humans. Okay, so one question is, how would you tell an AI, be nice to humans? Okay, so we've got a language here that represents lots of kinds of things in the world that tries to translate our thinking about things into a symbolic form that a machine can understand. But how would we talk about something like a be nice to humans statement? Well, it's, okay, so I think it's, well, what I've been interested in is trying to express, so within our language so far, we can express lots of kinds of things in the world. Like we can say, talk about, a chocolate chip cookie or something like that. We can't yet talk about, I want to eat a chocolate chip cookie. The question is, can we extend this symbolic representation we have of the world to also deal with this kind of everyday discourse? And I've been interested in this for decades, and I've done a little bit of work on it. I never really had a good use case. We finally have a good use case. And the use case is computational contracts. So the point is, when you write contracts, you write them in English, or maybe legalese, which is an attempt to write a slightly more precisely specified version of the contract. The question is, can we write contracts in code? And if so, what does the code look like? And so we've done a bunch of this, and it's kind of interesting, because you need certain kinds of constructs. You need to talk about the real world. We already have ways to talk about many aspects of the real world. You need some additional ways to talk about the real world. In the end, I think you need, the thing I've been interested in is building what I'm calling currently the symbolic discourse language, which is kind of a language that can symbolically express everyday things about the world. I mean, people have tried to do this before, but it's been about 400 years. I mean, back in the 1600s, this was a big thing, with philosophical languages and so on. It's quite amusing to look at what they did and compare the issues that they had in their world today. But anyway, different topic. There's a lot of many ways to die, but no technology was part of their ontologies. But so anyway, the one thing that is the goal is to make a symbolic discourse language in which you can represent sort of contracts as code. And this is, it's already the case that some financial contracts are already expressible in code in fairly simple ways, but even mortgages are not yet expressible and simple, as code. And it's interesting to think about how that might work. A place where people are very energetic about this is the whole blockchain world, which we've been, for better or worse, deeply involved in. I think the basic story, one thing when you have a computational contract, one of the things is that you can make it automatically execute. So, I'm sure we can ask it, we know about all kinds of things about the blockchain world. Let's say, blockchain token data, we could say something like, let's see, always a favorite, CryptoKitties. Let's see, the blockchain base for that is Ethereum. And this should give us some data about, okay, that's data about the, we could say, for example, who are the top holders of CryptoKitties? But the main point here is, it might take a little while, okay, there we go. Oh well, somebody owns 16% of all the CryptoKitties in the world. I'm sure this is some Zipf's law distribution or something. But anyway, so, in practice, by the way, when it comes to sort of autonomous execution of contracts, my impression is that what's going to happen is the low-price ones are going to be just done by random cloud providers like us. The very high-priced ones will rely on the legal system, and there's an intermediate zone that will probably actually operate in the blockchain cryptocurrency world. But in any case, one of the things of interest is to sort of create these computational contracts, a practical thing. One of the things that happens with computational contracts is you need a source of computational facts. You can have all these contracts and they say, if this happens, then that, et cetera, et cetera, et cetera. But somewhere you need to know, you've written weather insurance, somewhere you need to know, did it actually rain? that day, or whatever. And so actually we happen to be very much in the middle of this rather knotty problem of providing computational facts, because our Wolfram Alpha system is basically by far the world's largest collection of computable knowledge. And so I think I can say that 100% of people who are trying to make smart contracts that rely on external facts use our API. Now, that's a very interesting issue, because when you have a source of computational facts, and you have a whole bunch of these computational contracts, you have all sorts of terrible things that happen, because once a fact flips over in some way, there's this giant chain of dominoes of these computational contracts that will automatically execute. And in 100 milliseconds, a whole row of these contracts is executed, something will happen in the world. So it really is important to understand what level of certainty, what kind of facts you can deal with. And it's kind of funny, even with things that one might think of philosophically, sort of necessary truths about, things about numbers and things. Even there, it's not quite as obvious what to do, because there are things that may be computationally too complex to compute in certain times and so on. And when it comes to things like, who won such and such an election, at some point you have to say, because these computational contracts might depend on that. At some point somebody has to decide that, and then the domino effect starts and so on. And it gets even worse when you start thinking about, some of the things you guys were talking about with credit scores and things like this. There's an interesting set of issues about how you deal with sort of facts like that, and even more Internet of Things facts picked up from sensors. The sensor said the person walked 10,000 steps, so they should get a little bonus from their company, from the wellness program or something. Well, actually, they didn't. They just put their pedometer on some arm that's going back and forth. How do you tell that? There's sort of a trade-off between using machine learning to do anomaly detection and things about modeling the world. Interesting sets of issues. Anyway, one day there will be a big ecosystem of computational contracts. Interesting to think about sort of the relationship of government to that big ecosystem of computational contracts. The central bank that becomes, that is at some level an AI that's deciding how the money supply is going to work, and it's operating according to all kinds of computational contracts. It's interesting perhaps to think about, in this sort of highly automated way that the world works, what general principles should one have, and how should one express those general principles? Actually, it's just this little thought experiment. It's kind of interesting to imagine what happens, what's the sort of computational implications for democracy, for example. So, one of the things that happened 500 years ago or something was literacy, widespread literacy came in, and that enabled all sorts of forms of organization and government and so on. Well, we don't yet have widespread computational literacy. We certainly don't have widespread computational literacy at the level of the kind of computational language I'm talking about. I think we can have, and maybe sometime, I'm going to great effort to make that happen, but it will take a long time. Eventually we will have general computational literacy. The kids will be able to tell the AIs what to do, so to speak. And at that point, people will be able to express, for example, as a thought experiment, has all kinds of problems, but it's an interesting thought experiment. People will be able to express their preferences, not by voting for candidate A or candidate B. They'll be able to write some computational essay that expresses in some symbolic language, these are the things that I want to be true about the world. Okay, so imagine that you have a situation where you've got 100 million people who write their computational essays, and they hand them all in, and then they say to the big AI, okay, so figure out how the country should be governed or whatever. You're immediately thrust into all the traditional questions of political philosophy and so on about what to do under those circumstances. But it's sort of interesting to see that is actually something that the scenario I just gave you, minor versions of that will happen. Whether the full thing happens or not, I don't know. But so when talking about these computational contracts, one of the big ones to think about is, if we're making these AIs that are kind of running the world, what's the contract that we have with those AIs that are running the world? What's the analog of the UN, Declaration of Human Rights or something that should govern the AIs that are running the world? How should we express that? And what, even how do we think about doing something like that? Well, one thing you might say is, okay, there's got to be some mathematical principle that allows us to say what to do. Like, it could be some generalization of, Asimov's laws of robotics or something like this. It'll be some very simple closed set of principles. And when you talk to sort of people with a lot of sort of computer science energy, they'll often say there's going to be just some principle. It's just going to be some little thing, some little perfect rule that's going to determine how to make everything good happen in the world. I don't think that's going to work. And in fact, we can see that not only are there practical issues, but there's also theoretical reasons why that just can't possibly work. And one way to think about that is in terms of things like Gödel's theorem. So when in Gödel's theorem, the one thing, okay, so back 120 years ago or something, people thought that they would be able to write down an axiom system that described arithmetic, for example. And they write down this axiom system, and the axiom system puts enough constraints on things to say it's talking about the integers and nothing but the integers. Okay? And so very well defined, that's what Hilbert, people like that, believed would be the case. Okay, well, Gödel's theorem, when it came along in 1931, one of the things it showed is that you just can't do that. You think you've got an axiom system that says it's just about the integers and nothing about the integers, but that never works. There's an infinite hierarchy of patches that you have to put. There's sort of non-standard arithmetics that are things that still satisfy the axioms you had, but they're wild and wacky, and addition isn't recursive and all kinds of crazy things. So you say, well, let's put patches. Well, what Gödel's theorem establishes is that there's an infinite hierarchy of patches that you have to put on in order to get the integers and nothing but the integers. And it's the same kind of thing. When you have once you have a system that shows, I think I didn't talk about the important phenomenon of computational irreducibility. The question is, can you readily predict what this thing is going to do? And traditional exact science is very proud of predictability and saying, oh, we don't have to follow the Earth around a million orbits, we can just predict what it's going to do. That's a big calling card of exact science. Unfortunately, in the computational universe, there are many systems which are computationally irreducible, where you can't tell what they're going to do except by effectively just following each step to see what happens. That's a direct consequence of this principle of computational equivalence, because when you can jump ahead, what it's saying is the thing that's figuring out what's going to happen is smarter than the system itself. But if they're both equivalent, you can't do that. So computational irreducibility has a consequence, many, many consequences, but one of them is there are always unintended consequences. It's kind of, traditionally it's kind of there are always bugs, but it also means that in any system that can embed the kinds of things that we know really happen in the world, there will always be sort of unintended consequences. You try and put this patch, you try and constrain things in certain ways, it will always escape somehow, somewhere. You'll always have to go on patching. So this isn't terribly surprising. If you look at human legal systems, they have complicated, they're a big, thick, shelves of laws, so to speak. It's not like it gets to be just this very simple set of principles. And I think that's kind of what we're stuck with in terms of trying to express kind of our human goals for what we want the AIs to do. It's sort of there are all kinds of questions about how do you it's sort of the things we have to do are to express sort of computational representation of the essence of humanity as we want it to be. Probably not one of it. It's interesting for somebody like me. It's like, can you estimate how many countries there should be on sort of the back of an envelope? And that's which I don't think one can. But that's that sort of relates to the as we try and make this sort of computational representation of what humanity wants. How do we think about doing that, and how does that work from universally or not so universally, and so on? Well, okay, I probably lots of other things I could talk about, but I think my original question was the end of human exceptionalism, ? So to try to answer that question, I think we have believed that one very special feature of us is the intelligence that we have achieved. That's not special. It's kind of, this is the Copernican moment for that kind of thing. We can now see that with considerable clarity. We can see that there are, AI systems which we can readily perceive have many of the same attributes as our intelligence. I would claim, I believe the principle of computational equivalence establishes that notion of intelligence is actually much broader than us and the AI systems. It applies to lots of things in the physical world as well. So it's not, we can't hold out the idea that we're kind of the pinnacle of intelligence. I mean, it's worth understanding when we look at an AI, we look at the insides of what the AI is thinking, so to speak, even in some simple case like this machine learning thing. We say, what is it thinking? How do we tell a story about what it's thinking? How do we understand what it's thinking? Okay, so one of the issues is under what makes something understandable. So, for instance, here's an example I happen to just write about. This is about doing proofs. So this is about automated proofs. I happened to discover a number of years ago the simplest axiom system for Boolean algebra. It doesn't matter what the details of it are. The main point is that the proof that is correct is a thing that is 100 steps long. I printed in a 4-point type in the book that I made. And for 20 years, people have made efforts to understand this proof, and nobody can understand it. It's clearly correct. You can follow each step. Computers can follow each step. It's clearly correct, but we don't know why it's true. And the question is, what does it mean to have there be an explainable version of this proof? Okay? So this trade-off between computation and explainability is sort of interesting. I mean, we happen to in Wolfram Alpha, for example, gets used by the students of the world to do their homework and so on. And one of the popular features is, okay, not only do we give you the answer, but we'll also give you the steps to get to the answer. The thing to realize is those steps are completely fake. They have nothing to do with how the computer computed the answer. They're purely made, they are reverse engineered to be suitable for humans to understand what's going on. And so the question is, when you're presented with something like an automated proof of a result, can you get from that automated proof, can you get something that humans can understand? So, the lemmas that happened in that proof, if one of those lemmas had some long history, then it's sort of connected to the culture of mathematics. You say, oh, that was a lemma that was proved by Gauss in 1810 or something. So we understand that. But actually, these lemmas, as we have them, are just generated from scratch by the computer, and we don't get to have an understanding of these. So, sort of an interesting question: what constitutes being able to understand things? And so I think what one needs to realize is that there's kind of these layers of abstraction that get built. And we're just saying, okay, there are these random lemmas that you can pick out of the sort of computational universe of all possible lemmas. That's not something that we humans can sort of get our minds around. What tends to happen so actually, even if you think about the advance of knowledge in the world, there's more and more that gets known, and so you might think education would take longer and longer and longer because there's just more and more that's known, there's more and more to know in the world. But that isn't the case, and the reason it isn't the case is because there are layers of abstraction that get built. You don't have to know all of those details because some general principle got discovered that you just learn that principle and then you don't need to know all of those detailed facts. And it's the same thing with this sort of understandability issue. It's what layers of abstraction can you build? So a version of that, sort of interesting, is language is a good example of that. Like you say, well, there are all these things and they all have 4 legs, and eventually we'll invent the word table that describes those things, and then we can start building more concepts on top of that. And in fact, it's sort of interesting, there's this weird co-evolution between the forms of abstraction that we generate in, for example, language, and the actual the world that we live in. Because once we have an abstraction, like a table, lots of people make tables. And so then the world is more about tables. And then once we've invented an abstraction, we sort of build our world to make use of that abstraction. So it's this sort of circle between the things that we figure out and the way we build our world. And so it's one of the things that happens in, when we look at sort of the AIs, so to speak, they are also coming up with, in a sense, abstractions. The discrimination that's being used in this image identifier, there are lots of discriminations that are being used. Some of them we can identify. Some of them are like, it's a dark picture, it's a light picture. But some of them are things for which we have no words in our language. But they might be things that are very, very useful for distinguishing things in the world. We just don't happen to have words for them because our cultural history has not led to the development of that abstraction. So it's sort of this whole question about sort of pulling how you make things explainable is all connected to this question of how you build layers of abstraction. It just so happens that my life activity of building computational languages is also about deriving layers of abstraction, because what computational languages are things where you're taking sort of all possible computations and you're figuring out what are the primitives, what are the abstract primitives that are worth including in your language. It's very similar to, I mean, language designers human languages don't get designed by people typically. Computational languages do get designed by people, and people don't yet realize that for human languages, it's not totally clear how much the structure of human languages affects how people think about things. For computer languages, it is completely clear that it is unbelievably important how the language is structured in determining how people think about things. So it's an interesting, that's why I think what I do is somehow important, because one's in designing a computational language, you're determining how lots of things get thought about, and that's an interesting thing to do. But anyway, so the question of end of human exceptionalism. So we're the smartest things in the universe. That's gone. But we have, in a sense, we've got this particular corner of the computational universe that is very special to us, that has many details that come out of sort of the particular history of our civilization and so on, and that so in a sense we have great exceptionalism because we have this amazingly special corner of the computational universe. There isn't something abstractly special about it. It is simply special because it's the one we live in, so to speak. And there are a bunch of questions that one could start thinking about okay, so now we've got these we've had nature for a long time that we've sort of coexisted with, and nature we now believe has sort of intelligence of a kind a bit like, that's just like the intelligence that we have. We've successfully coexisted with nature. Now we happen to be creating another alien intelligence, which is the AIs, and we think we have a bit more control over the AIs than we do over nature. And so we then have to think about, how do we exercise that control over the AIs? And so, well, lots more we could talk about, but I should stop here because